In Formula One racing, the technical aspects of calculating average speed have reached new limits of optimization that allow the pit crew to work out in great detail the mathematics of the car's speed. Hi, my name is Tom Atwater, and that's what we'll be examining in today's lesson, average speed and limits. Let's start by talking about average speed. A moving body's average speed during an interval of time is found by dividing the distance covered by the elapsed time. Let's try an example here. A rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of the fall? The equation for the free fall of a dense object close to Earth is y equals 16t squared. So y equals 16t squared. Now, what we need is the distance, which is the change in y, delta y, covered in the change in t, delta t, or in this case, it's 2 seconds. Now, delta y, the change in y, would be equal to 16 times 2 squared minus 16 times 0 squared. So delta y is going to equal 16 times 4, or in other words, 64. And that's 64 feet in 2 seconds. All right, that reduces to 32 feet per second. All right, let's see what we could do if we wanted the speed of that rock in that example at the very instant of 2 seconds. So in this particular case, we want to find the speed of the rock at the very instant of 2 seconds. In that case, what we have to look at is that the speed is the delta y divided by delta t in the following formula. It would be equal to 16 times 2 plus h quantity squared minus 16 times 2 squared, and that's all over h. And what we're looking at is what's going to happen to this formula as h gets very close to 0. In fact, we're going to look at what's called a limit as h goes to 0. Well, before we do that, realize that we can't actually calculate this when h is equal to 0, because that would make the denominator 0 and it would be undefined. So we can, however, evaluate it as h gets close to 0. Now let's look at the following table that will help us to see what happens as h approaches 0. Starting with h is equal to 1 and then having h get closer and closer to 0, you will see that the average speed for that interval gets closer and closer to 64, or in other words, the same limiting value that we saw earlier. So now what I'd like to do is look at this algebraically. So I want to take a look at that equation that I had before, which is delta y over delta t is equal to 16 times the quantity 2 plus h squared minus 16 times 2 squared over h. And now what I want to do is expand this and simplify it out. So delta y over delta t is equal to, Well, of course, this is a binomial squared, and so this would be 2 plus 4h plus h squared. So 4 plus 4h plus h squared minus 16 times 4 all over h. And now we have to take the 16 and distribute it into there. So we'll get 64 plus 64h plus 16h squared minus 64 all over h. The 64s and the negative 64 here add up to 0. And then I can factor an h out of each of these terms. So I have h times 64 plus 16h all over h. Now, those h's cancel out, and I have simply 64 plus 16h. And now, what we can say is, or clearly see, that as h goes to 0, right here, that this term, 16 times h, will go to 0, and therefore the average speed has the limiting value of 64 feet per second, and that's as h approaches 0. Great. Now, the concept of taking smaller and smaller time intervals and getting closer and closer to the time of t equals 2 is the concept of a limit. So let's take a look at that definition. Let c and L be real numbers. The function f has limit L as x approaches c if, given any positive number epsilon, there is a number delta such that if you can get x within delta of c, then f of x will be within epsilon of L. Theorem 1, properties of limits. If L, M, C, and K are all real numbers, and the limit as x goes to c of f of x is equal to L, and the limit as x goes to c of g of x equals m, then we have the sum rule that tells us the limit of the addition of the sum of those two functions, f of x and g of x, is equal to the sum of their individual limits, L plus m. We have the difference rule, which tells us that the limit of the difference between f of x minus g of x is the difference between their two limits, L minus m. The product rule tells us if we're taking the limit of the product of f of x and g of x, that that's going to equal the product of their limits, L times m. The constant multiple rule tells us that if we have the limit of k, which is a constant, times f of x, then that's just going to equal k times the limit of the function, in other words, k times L. The quotient rule, that is, if we're taking the limit of f of x divided by g of x, that's going to equal the quotient of their limits, that is, L divided by m, provided, of course, that m doesn't equal 0. And last, we have the power rule. And the power rule says that the limit of a rational power of a function is that power of the limit of the function, provided, of course, that L raised to the power r divided by s is a real number. So I think the best thing to do now is to try some examples so that you can see how to apply these properties. So determine the following limits by substitution and then support it graphically. We have the limit as x goes to 1 of the polynomial x cubed plus 3x squared minus 2x minus 17. And our second problem will be the limit as y goes to negative 3 of y squared plus 4y plus 3, all divided by y squared minus 3. Let's take a look at that first example. we have the polynomial, and we want the limit as x goes to 1. So substitute 1 in for x. 1 goes there, 1 there, and 1 there. Well, of course, that's going to be 1 plus 3 minus 2 minus 17. And that is going to give us a limit of 15. When we look at the graph, we can see down here that we substitute in x equals 1, and the graph yields y equals negative 15. So now let's take a look at the second example. What happens this time is when we plug in negative 3, we have negative 3 squared, which would be 9, plus 4 times negative 3, which is negative 12, plus 3, all over negative 3 squared, which is 9, minus 3. But if we look at the top, 9 minus 12 plus 3 equals 0. So this limit is 0. When we look at the graph, of course, remember that your graphing calculator uses y and x as the normal order, which is to say that I had to enter y as a function of x. So this time, really what I'm going to do is look down here and say, okay, as x approaches negative 3, the value of, in this case, y, approaches 0. And so again, graphically, we are supported by what we had found by using the method of substitution. But now, let's try another example, and this time determine the limit graphically first, and then support it algebraically. So let's take a look at the limit as x goes to 0 of 5x cubed plus 8x squared over 3x to the 4th minus 16x squared. So the first thing I want to do is look at that graph. So what we're interested in is as the graph, as x approaches 0. So when we look at this, right here, as x is approaching 0, what we see is that that's equal to negative 1/2. And the question will be now, what happens when we look at this algebraically? So let me switch to here, and let's work with this problem to see. So the first thing I can do here is to factor both the top and the bottom. That is to say, I can factor out an x squared on the top, and that's going to leave me 5x plus 8. And then on the bottom, I can also factor out an x squared, and that will leave me 3x squared minus 16. And then what I'm looking at is the limit as x goes to 0 of 5x plus 8 over 3x squared minus 16. And of course, as we can see, this and this will both go to 0 as x approaches 0. So what we'd be left with is 8 over negative 16, which of course reduces to negative 1/2. So sometimes it's important to look at it graphically and then algebraically, or sometimes it might be the other way around. Now, it's important that you look at when the value is being approached from the left as well as from the right-hand side. And we can determine this evaluating what we call one-sided limits. Let's take a look at the definition for one-sided limits. A function f of x has a limit as x approaches c if and only if the right hand and the left hand limits at c exist and are equal. In symbols, what we say is the limit as x goes to c of f of x is equal to capital L if and only if the limit of f of x as x approaches c from the right-hand side is equal to capital L. And as it approaches from the left side of C, the limit is also L. So in both cases, we get a limit, and the limit is the same. So let's try an example. Given that C is equal to 2, we have f of x is equal to 3 minus x when x is less than 2, and it's equal to x divided by 2 plus 1 when x is greater than 2. Draw the graph of f, determine the limit as x approaches C from the positive side and the limit as x approaches C from the negative side, and then answer the question, does that limit exist? And if so, what is it? And if it doesn't exist, explain why it doesn't exist. So the first thing we're going to do is draw the graph. So let's take this part here and graph it. We know that the y-intercept is 3 and that the slope is -1. So we would draw a line that goes through those 2 points. And when it comes down, there's going to be an open circle at 2 because we have x is less than 2. Now, for the second part of this graph, we need to, again, draw a straight line. And in this case, it's an open circle up here at 2. And the slope is 1/2. So it's going to be a slightly flatter line going out in that direction. Well, what does that mean? Well, it means that we have a right-hand limit, which is equal to 2. In other words, as we approach from this side, it's approaching 2. And the left-hand limit, that is, as we approach from this side, the limit is 1, which means the limit doesn't exist because even though there's 2 limits, they are not the same limit. So therefore, this does not have a limit. Let's move on to the sandwich theorem. If the value of f is sandwiched between the values of 2 other functions, in this case g of x and h of x, for all x not equal to c, in some interval about c, then and the limit of g of x as x goes to c is equal to the limit of h of x as x goes to c, and they are both equal to L, then the limit as x goes to c of f of x will have that same exact limit too, in this case, L. I think the best way to illustrate this would be to look at an example where we use both a graph and then the sandwich theorem to confirm what we see from the graph. So let's take, for example, finding the limit as x goes to 0 of x squared times sine 1 over x. So let's look at the graph first. The graph itself for x squared sine x is this graph right here, which we can see coming in and then expanding back out over here. And what I want you to notice is that it is sandwiched between 2 graphs, which are parabolas. This is y equals x squared and y equals negative x squared. And of course, what's happening then is that this limit is approaching 0. Well, now let's take a look at this by using the sandwich theorem. So we're going to look at the limit as x goes to 0 of x squared times sine 1 over x and look at it from the sandwich theorem point of view. So what I have is the first thing. We can separate out these two and say that this is the same as the limit as x goes to 0 of the absolute value of x squared times the absolute value of sine 1 over x. And then what you can remember is that the sine of theta always ranges between 1 and -1. And what that means is the absolute value is going to range between, or is going to be 1. So we can say that this is going to be less than or equal to just plain old x squared times 1, which of course means that it's simply equal to x squared. And that's where the sandwich theorem comes in, because we can graph y equals x squared and y equals negative x squared, and say that this is going to be sandwiched between those two values. And in that case, they are both approaching a limit of 0, which means that this must also be approaching a limit of 0. Okay. Next, let's take and have you try a problem. What I want you to do is find the limit graphically and then support it using the sandwich theorem, the limit as x goes to 0 of x times the sine of x. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's see how you did on the problem. Here's the problem that I asked you to do, the limit as x goes to 0 of x sine x, and here's the graph. The graph is, of course, sandwiched between the absolute value of x and negative the absolute value of x. Now, in terms of looking at that, and of course, those are both have a limit of 0, so that's what we would expect to find when we use the sandwich theorem. So let's look at this algebraically now. So if we want to look at the limit as x goes to 0 of x sine x, what we can say is, of course, sine x, that is going to be between positive 1 and negative 1, which means that I can write this as the negative absolute value of x between x sine x and the absolute value of x, like this, which of course means that we're looking at this and this to find out if they have the same limit, if they have a limit, and if the limit is the same. And of course, the limit is 0 for both of them, and therefore we can say that that limit up here is 0. And that's how you can use the sandwich theorem to algebraically find the limit. All right, well, great. In this particular lesson, we learned about limits and using the sandwich theorem algebraically and to support our work graphically. Be sure to work the exercises that your teacher assigns, and we'll see you next time.